We're going to take a dynamic programming algorithm that fails a 9-second time limit and replace it with a solution that finishes in 30 milliseconds. The objective is to evaluate an integer array and extract a subsequence that yields the absolute maximum sum. But every valid subsequence must satisfy two strict rules. First, a distance constraint. Every consecutive pair of chosen indices must be separated by at least k steps. Second, the values of those elements must strictly alternate. They have to zigzag. Every step must oscillate from a lower number to a higher number, or vice versa. Ties are not allowed. In an array of 3, 5, 4, 2, and 4, with a k of 1, the optimal pick targets indices 0, 1, 3, and 4. The values, 3, 5, 2, and 4, step up, then down, then up, totaling 14. The difference between an algorithm that passes and one that times out lies entirely in how we structure the search space around these two constraints. The foundational approach uses dynamic programming, processing the array indices from right to left. For every index I, we store a pair of values. One tracks the maximum sum of an alternating subsequence starting at I, where the first step goes up. The other tracks the maximum sum where the first step goes down. To populate these, we look at every future index C that is at least k distance away. If the value at I is less than the value at C, we are moving up. We add our current value to the downward starting maximum already stored at C. Symmetrically, if the value at I is greater than the value at C, we are moving down. We add our current value to the upward starting maximum stored at C. Capturing both the upward and downward trajectories simultaneously ensures that every valid alternating sequence is accounted for in the final result. This scaling table identifies the failure point. At 100,000 elements, the calculation time leaps to 9.3 seconds. The system hits the time limit and halts. The bottleneck is the nested inner loop. For every single index I, the algorithm performs a linear scan across every eligible future element C to check our constraints. We can translate the first conditional branch of that loop into a mathematical query. Among all eligible elements, find the maximum downward sum where the array value is strictly greater than our current value. The second branch asks, find the maximum upward sum where the array value is strictly less than our current value. The DP logic is correct, but executing it via linear scans creates 10 billion operations at full scale. To pass, we must execute these max-range queries in logarithmic time. The segment tree is the specific tool required to break this linear scanning bottleneck. This binary structure holds aggregate data, the maximum value, over contiguous array ranges. Leaves hold raw values. Parent nodes store the maximum of their two children. To modify a value, we use a point update. We walk one direct path from root to leaf, change the value, and recalculate the maximums for every node on the way back up. Because we visit only one path, updates complete in O of log n time. To find a range maximum, we query the tree. Nodes entirely outside the target return 0. Nodes completely inside return their stored max. If overlapping, we recurse into the children. This logic ensures we check at most 4 nodes per level, keeping the query time strictly logarithmic. Replacing an O of n scan with this tree structure changes the computational budget of our inner loop from linear to logarithmic.
To apply this to our DP, we have to change our perspective. We stop indexing the tree by array position and start indexing it by the raw element values themselves. We map 2 empty segment trees across the entire numeric range. The best downward sequence is a range max query in the second tree, searching above the current element. The best upward sequence queries the first tree for values strictly below the current element. While indexing by value handles the zigzag rule, we still need a way to enforce the k distance requirement. We do this using a sliding release. As we process the array backwards, a second pointer follows at a distance of k. Only when this trailing pointer reaches an index do we insert that element's DP results into our trees. This ensures a value is only available once it becomes eligible. This combination enforces both the distance and the alternation constraints without ever needing a nested loop. Let's trace example 2. We start at the end of the array, index 4, value 4. The trailing pointer hasn't entered the array yet. Both queries return 0, so our current DP state is simply the value 4. At index 3, value 2, the trailing pointer releases index 4 into our trees. Our query for values greater than 2 finds the 4 we just released, giving us a sum of 6. At index 2, value 4, we release index 3 into the trees. We query for values less than 4, find the 6 we stored at index 2, and update our local maximum to 10. At index 1, value 5, index 2 is released. Our downward query searches values less than 5, checking the tree and returning a 6. Finally, at index 0, value 3, we release index 1. The queries for values above and below 3 return 11 and 6 respectively. Adding our current value of 3 to 11 gives us 14. 14 is our final answer, corresponding to the sequence 3, 5, 2, 4. Note how the empty trees naturally return 0 for our first calculations. This means the base case, a single element subsequence, handles itself automatically without extra code. The operational inference is stark. We've reduced a linear scan of 100,000 elements to 2 logarithmic queries, cutting the total work from 10 billion operations down to 3.4 million. In terms of actual time, that is the difference between a 9-second failure and a 30-millisecond pass. To gain this speed, we traded a small amount of memory to house trees that span the entire range of potential values, moving our space complexity to O of n plus v. Trading spatial overhead for a massive reduction in time complexity is a core indicator of competitive programming mastery. This lesson applies well beyond this specific problem. If your dynamic programming has an inner loop searching for an optimal value under a constraint, you are likely looking at a range query. The constraint in the problem dictates what the tree should index by, whether that's value, time, or position. The data you need to find, a maximum, a minimum, or a sum, dictates the architecture of the tree itself. You can apply this heuristic to find total sums using Fenwick trees, or frequency counts using segment trees. Once you recognize this structural pattern, you stop trying to optimize linear loops and start replacing them entirely, turning time limit errors into instant accepts.